Now we want to look at applying these ideas to radiometric dating.
So previously we saw that half-lives characterize how quickly different isotopes decay, and that can allow us to understand how much is left after a certain amount of time. It can also allow us to work backwards in many ways. And so nuclear half-lives are constant. It's a first-order process. That's true of any first-order process. And so what we can do is we can use that fact to figure out, based on if we know how much we started with, how much nuclear material we started with, and how much we have now, we can use our equation, we can use the equation to figure out, or half-life equation, to figure out how much time has passed. And so we can kind of rearrange the half-life equation we had into what we would call the radiometric dating equation. It's just a rearranged version of it. Just move that n0 over. But it allows us to figure out the time that how old an object is, how much time has passed since that isotope got inside of it. So one of the main types of dating we use is carbon-14 dating. And the idea of carbon-14 is not a stable nucleus, so carbon-14 is unstable, but it exists, it's formed in the atmosphere from radiation coming from outside the solar system. So you have high energy particles and rays and stuff that come into the atmosphere. This is one of the purposes of the atmosphere, that it takes the brunt of that radiation. And it leads to the creation of, say, free neutrons, and then those hit nitrogen-14 atoms and become carbon-14. So this carbon-14 exists in the atmosphere. It's unstable, but it has a half-life on the order of a couple thousand years, so it's out there. But these atoms are out there in the atmosphere, and so what ends up happening is it gets consumed and incorporated into living things. So there's carbon-14 in the atmosphere that goes into, say, plants. Animals eat plants, and so they then have carbon-14 inside of them. You have carbon-14 isotopes inside of you right now that are potentially undergoing nuclear decay. And so they're in there, you have that sort of level. And so as long as you live, as long as you're alive, you keep eating things, food that was exposed to the atmosphere. So you take in carbon-14, that carbon-14 somewhat decays, but eventually you hit a sort of constant amount, right? You keep eating, you keep breathing, carbon-14 gets inside of you, and then that carbon-14 decays. And you reach a constant level of carbon-14 based off how much carbon dioxide is in the atmosphere. Well, when you die, you stop eating. And so the carbon-14 no longer gets into the organism. Okay, so say you have a fossil, there will be carbon-14 that's in the organism when it dies, but no more will go in after it dies. And so you just start to lose carbon-14 by decay. So there will be some left, and if you can figure out how much is left based off how much would have been in the organism when it was alive or when it died at the time of its death, you can figure out how many years have passed since it died. So one half-life for carbon-14 is 5,730 years. So with that time, we can figure out how much is left. You can then basically turn that into how many half-lives have passed and then turn that into a time. There are restrictions. You can only it has to be kind of old. You can't figure out if someone died like yesterday using this, but they can't be super old. It's about 70,000 years old is kind of our limit for carbon-14 dating. So let's see how this works. An artifact is found to have a level of carbon-14 that is 37% of that in living organisms. How old is this artifact? So you found a fossil, plant, some sort of object that was previously living. And so now let's see how old was it? Basically, when did it die? Which is presumably then how long it's been in the ground. If we want the age of an artifact, okay, so this is going to be one of the first times we've ever dealt with this. There's not really much context that we would see else outside of radiometric dating. The other thing that we can see is that there's a carbon-14 explicitly referenced. Carbon-14 dating is one of the most common radiometric datings because it allows us to date fossils and things that were alive, people, animals, plants, anything like that. And especially humans tend to use formerly living things like trees to make a basket, say, or to make a piece of a tool or something like that. And any of that's fossilized, it was alive. You can still date when that, say, tree died to get turned into a tool. And so we can use it for anything that was ever living, that it was exposed to the atmosphere. So our carbon-14 dating equation, or our radiometric dating equation really looks like this. And we want the T without the subscript. That's always the equation, the value we're looking for is going to be that T. So we got some other variables. I need the NT over N0. One of the reasons why we rearrange the equation is that in the context of radiometric dating, usually this could be two different variables, but it's more often represented as a percentage, as this ratio here. So the 37% that we're looking at means that the ratio of the amount of nuclei at time t is 37%, the nuclei that were initially there, which means we get 0.37 as that ratio, or 37%. So we just would a decimal or kind of a ratio representation or that percentage representation. So 0.37 there. And then T1/2, that's our half-life. You'll note it's not given in the problem, but we're told it's carbon-14, and we can always look up the half-life for any isotope. Carbon-14 is a very common one. That's 5730 years, 5,730 years. But if it doesn't matter what it is, there's other types of dating that you can do, and you can always look up a half-life. It doesn't matter what the isotope is, you can look them up. They're all figured out, and you can use that information. All right, so if we actually want to plug some things in, here's the equation we have. So we're going to plug in the variables we had. The NT over N0 was 0.37, and our half-life was 5,730 years. So I want to solve for T, which is currently in an exponent. In order to isolate that value out of the exponent, I need to use logarithms. So I take the logarithm of both sides. In this case, I've used a natural logarithm. You can use any base logarithm you want. So I've used a natural logarithm. What that then does is when I take that logarithm, I take a logarithm of something with an exponent, I can take that exponent and bring it out in front as multiplication. And the reason why I can then see that it's out there, that fraction that was in my exponent is now in the front as multiplication. And that's I can now process that using algebra. Right, so I can now, in terms of isolating the T, it's just a matter of moving things around, right? Basically divide both sides by the ln 0.5, multiply by the 5,730. Those logarithms of a number is just a number. I can evaluate what all of that is, and I get that the age is 8,200 years. And so this would tell me how old, or basically it tells you when that living thing died. So because it only has 37% of the carbon-14 that you would expect in living things, what that would therefore imply is that it died 8,200 years ago, which since there's already some significant or some error on that, we only say 2 sig figs on the years, that's when it died. That's probably close to when it lived.
Participation 421, question 2. What percentage of carbon-14 is still in the leaf of a plant that died 15,000 years ago? Second question on participation 421, due Tuesday, April 21st at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, what percentage of carbon-14 is still in the leaf of a plant that died 15,000 years ago?
So with radiometric dating, we are limited by what sort of time frames we can look at based on the isotope we're looking at. So, if we think about after a lot of half-lives passed, there's still some nuclei left, but not a lot. So for example, at 12 half-lives, 0.024% remains. Okay? After 13 half-lives, 0.012% remains. Those are really similar numbers. And if you're measuring, the radioactivity or how many nuclei are left in a rock, that's pretty hard to distinguish those two numbers. You would need really, really high precision to distinguish those. So, you're going to be limited based on how many half-lives back you can trace. So when it comes to living things, carbon-14 works really well, but you can only do, say, 10, 11 half-lives, so you get to, say, 70,000-ish years. You can't really go much older than that on living things using carbon-14. So if we want to go to older dating, we just use different isotopes. So for example, potassium-40 to argon-40. So we can use both. Some of the facts on the half-life is going to be on the order of hundreds of thousands of years. So we can get really old, much older rocks using this information. We can also use a little bit of the chemistry. Argon is a noble gas. So when potassium-40 decays, it creates argon-40. And so there would be argon-40 potentially in the rock. The thing is, argon is a gas, a noble gas, so it is not in chemicals. So argon-40 does not enter rocks unless it gets trapped in the rock as a gas, or gets trapped in the rock when the rock is liquid. So what that would imply is that the amount of argon-40 in a rock is based on when that rock was formed out of magma. So if there is also potassium-40 in the rock, that potassium will decay and turn into argon. So what you can do is measure how much argon is in a rock. That gives you information then on how old it is, because you know how much would have been in the rock based on it being exposed to the atmosphere. And if whatever additional argon it has in the rock implies that all of that additional argon came from radioactive decay since it existed as a rock, right? Because basically it turns into the argon and the argon just gets stuck in the rock. So we can do, say, rocks that are hundreds of thousands of years old using this data. If you want to go even older than that, you need to use fancier methods. If you remember when we looked at that table of half-lives, uranium-238 was billions of years. So uranium-238 decays into what's called a decay series, right? Uranium-238 decays. We looked at it at the end of the last set of videos, and then it creates the nucleus. The daughter is still unstable, so that decays. The daughter is still unstable, that decays, da, 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 da. And so eventually it becomes lead-206. And so uranium can get into rocks that are called zircon rocks. This is a special kind of rock, or chemistry of rock. And so the uranium can be in there. Basically, the uranium's in there. And then the rock forms, and then eventually the uranium starts to undergo decay, and you get into that many decay sequence. And eventually you may create some lead from nuclear decay. But lead does not chemically incorporate into these rocks. So any lead that's in the rock has to come from the nuclear decay of uranium that got into the rock when it formed, right? When it was lava. And so what that allows you to do is you can do like really complicated measurements of a lot of different isotopes along that sort of decay pathway. And then you can get a lot of measurements, and that's how you can get fairly accurate measurements of really old rocks. They have to be this particular type of zircon rock, which is not, so you can't just date any kind of rock. But that's how you can date things that are hundreds of millions of years old up to like billions of years old, just by figuring out all of those different, you can look for all the different nuclei that are present in that rock, that correspond to points along that decay pathway, because the lead couldn't get in there without when it was lava. So all the lead that's present has to have come from a nuclear process.
Two questions on participation 421. You want to find both those questions, get them answered, and get those answers submitted over on Blackboard by Tuesday. Wednesday night, we got the midweek 14 homework. Lab technique presentation is due this week. If you're doing it on campus, you need to come on Wednesday. Otherwise, you don't need to come. We don't have any lab activity this week. If you're making a video, that's going to be due on Thursday, the 23rd. We do have a second set of videos this week, finishing up chapter 21. Some more kind of applications of nuclear chemistry. If you have any questions about anything, let me know. Otherwise, enjoy the rest of your day. Take a look out, keep an eye out for the answers to the participation questions. I'll go live on Tuesday night. Otherwise, enjoy the rest of your day. I'll see you later. Bye-bye.